So area between curves. Let's just do some examples. So I want to find the area between these two curves. What if I got here y equal to x squared minus 2x and y equal to 3x. So let's go ahead and see what these look like. So x squared minus 2x is a parabola opening upwards with an x-intercept of 0 and an x-intercept of 2. Right? You can factor this as x times x minus 2. So it looks like this. And y equal to 3x is a straight line going through the origin, looks something like that. And so we were trying to find this area here. So what we need to do is you need to integrate from the first point of intersection to the second point of intersection of the top function minus the bottom function. And basically the idea here is, once again, we're using just rectangles. What I'm actually really kind of thinking of is, let's say there's a little rectangle right here. Really, I'm thinking of drawing all the rectangles. I just don't want to draw all the rectangles. And the area of this rectangle, well, we know how to find the area of a rectangle. It's base times height. The base is really small. The base is dx. The height is the top function minus the bottom function. So that's the height, right? And depending on where we are, right? Like if we're at, specifically if we're at x equal to 1, the height is going to be 3 minus negative 1. But in general, the height is the top function, 3x minus the bottom function, x squared minus 2x. So that's the area of this one rectangle. But then we add up all the rectangles, meaning we integrate. So we integrate from here to here, the top function, which is 3x, minus the bottom function, which is x squared plus 2 minus 2x. Now, a couple things before we do this. How do we know which one's which? What if we, I mean, obviously, I have graphed it. You can literally see, oh yeah, the straight line is the one that's bigger. Or as she said, it's more in the y direction, right? When you're doing top minus bottom, the top one is the one that's more in the positive y direction, and the bottom one's the one that's not as much in the positive y direction. But an easier way to do this, or a way to do it without actually having to graph the things, is, well, first you have to find where they intersect. So how do you find where two functions intersect? You set them equal to each other. So we're going to set x squared minus 2x equal to 3x. Subtract the 3x, you get x squared minus 5x equal to 0. Factor out an x. So x times x minus 5 equal to 0. So our points of intersection are x equal to 0, x equal to 5. So those are going to be our limits of integration. Now, how can we tell which function is the top function, or the one that's higher up or further from the more the positive y direction? Well, these functions, x squared minus 2x and 3x, have the same value at these 2 points. So when x is 0, y is 0. When x is 0, y is 0. So we get the point 0, 0. When x is 5, y is 15. When x is 5, y is 15. But then, anywhere in between those 2 points where they're not equal, one function has to be larger. And so you can pick any number between 0 and 5. I'm going to pick 1. And I'm going to ask which one of these is bigger. Well, if I pick 1, 3 times 1 is 3. 1 minus 2 is negative 1. That one's bigger. That's it. So that's how we can figure out which one's bigger without graphing. So the area between these two curves is going to be the integral from 0 to 5 of 3x minus x squared minus 2x dx. So that's how we set it up. Are there questions about the setup here? Okay. The rest of these, and so I will say, a lot of the time, not always, but a lot of the time, when you're actually finding area between curves, often the functions you're actually integrating are not that complicated. Like we've been doing a lot of really complicated integrals with u sub and integration by parts or one, right? This one's just a straightforward powers of x, right? This is not super hard to integrate. So yeah, let's go ahead and do it on this side. So the integral from 0 to 5 of 3x, what was it? I'm going to distribute the minus sign, minus x squared plus 2x. And then if it were me, before I actually integrated, I would combine the 3x and the 2x to get the integral from 0 to 5 of 5x minus x squared. And now we'll want to differentiate. We're going to get 5x squared divided by 2 minus x cubed divided by 3 between 0 and 5. Plug in 5. 5 times 5 squared is 5 cubed over 2. Plug in 5 cubed over 2, over 3, sorry. Minus, plug in 0, you get zeros. And so the reason I wrote it like this is, well, is so that you can see that if you want, you can factor out the 5 cubed before you add these fractions together. So I can rewrite this as 5 cubed times 1/2 minus 1/3, which I think is easier to deal with. So then this becomes 5 cubed is 125. 1/2 is 3/6. 1/3 is 2/6. So you have 125 times 1/6, which is 125 over 6. And that would be the area between these two curves. Questions, comments, concerns? See, I had one and then it went away. Let me, yeah, okay, fine. I wanted to do one, but let me see. I know I have an example here somewhere. Sorry, one sec. Let me grab something. Sure, there should be one there. Definitely. Okay, cool. Let's look at this one. I want to find the area between these two graphs. And hopefully, yeah, this is not terrible. Okay. F of x equal to 3x cubed minus x squared minus 10x. And g of x equal to negative x squared plus 2x. And so I have a vague idea of what these graphs look like. I know this is a cubic function. F of x probably looks vaguely like this. I don't know exactly. This is a downward opening parabola. So maybe it looks, I don't know, something like this. And so I see the potential for 1, 2, 3 points of intersection, where between the first 2 points, one function is on top, and between the next 2 points, they actually switch and the other one's on top. So long story short, I'm usually going to start off trying to find the area between curves by finding where the curves intersect, because that's going to tell us what our limits of integration are. So let's go ahead and set f of x equal to g of x. So let's see, I've got 3x cubed minus x squared minus 10x equal to negative x squared plus 2x. Bring everything to the side that you want. I'm going to always pick the side with the highest power that has a positive leading coefficient. So I'm going to bring everything to the left. So I'm going to have 3x cubed minus x squared plus x squared is 0x squared. Great. And then negative 10x minus 2x is minus 12x. 0. Factor out of 3x. I'm left with x squared minus 4. Factor some more. We got x minus 2 times x plus 2. So let's look at my points of intersection are x equal to 0, 1, 0, 2, and negative 2. All right, so here's what I've got. Oh, interesting. Okay. Anyway, so you can plug in to find the y values you want. Like I plugged in 0 and got 0. If you plug in 2, you do get also 0 for each of these. If you plug in negative 2, you get negative 4 minus 4 is negative 2, something like this. So I know that the parabola looks, I don't know, something like this. And the cubic looks maybe like that. You don't have to know what these graphs look like. I'm just showing you so that you will believe me when I say the next part. So between negative 2 and 0, how am I going to figure out which one's bigger? Well, I'm going to pick a point between negative 2 and 0. I'm going to pick negative 1. So which is bigger? F of negative 1 or g of negative 1? Well, f of negative 1 is 3 times negative 1, which is negative 3, minus 1, minus 10 times minus 1 is plus 10. So f of negative 1 is 6. And g of negative 1 is, let's see, negative 1 minus 2 is negative 3. So between negative 2 and 0, f is bigger than g. So far, part of the area calculation is going to be the integral from negative 2 to 0 of the bigger one minus the smaller one, f minus g. Now, something else to be on the lookout for, they don't always change when you go to the next part. So it's not a guarantee that the next section from 0 to 2 is going to be g minus f. It is going to be that here, but it's not guaranteed to be. You could have a function, you could have something silly where one function did this and the other function did this, and they intersected 3 times, but the top one was always the same here and here. So just be aware that like they don't always change which one's on top. Here it is going to change though, because if we look at f of 1 and g of 1, f of 1 is 3 minus 1 minus 10, which is negative 8. And g of 1 is negative 1 plus 2, which is 1. So g is bigger between 0 and 2. So that's how we would calculate this, the area bounded by these two curves. Because the reason we're doing this is so that all the area gets counted as positive. Right? We want to count this area as positive and this area as positive. If you just did the integral from negative 2 to 2 of f minus g or g minus f, you would get the net area between the two curves. And one would be positive, one would be negative, but they wouldn't be right. Are there questions about this setup? do want to stress for this problem, you didn't have to graph it at all, right? We could have said they intersect at 0, 2, and -2. Between -2 and 0, we can see that f is the bigger one. So that's our integral. Between 0 and 2, we see that g is the bigger one. So that's our integral. We didn't have to actually graph it. It's nice to graph it. The graph helps you see things, but it's not required. That might not be true for the next problem. The next problem, we might actually have to graph it. So that's why I'm saying, if you have an opportunity to not graph a thing, take it. We should calculate the integral. It is worthwhile to calculate. So let's see what we get here. So I get the integral from -2 to 0 of, we said f minus g, so that's going to be this minus this, so 3x cubed minus x squared minus 10x minus -x squared plus 2x plus, and then the integral from 0 to 2 of g minus f. So g minus f is just going to be -x squared plus 2x minus all of that. 3x cubed minus x squared minus 10x. All right, I think we should make our lives easier, so let's combine this. It's going to be the integral from -2 to 0 of 3x cubed minus x squared plus x squared is 0x squared, and then minus 10x minus 2x is minus 12x. And then this should just be the opposite integrand, right? If you do f minus g and get this, g minus f should be the negative of this. So g minus f should be the integral from 0 to 2 of 12x minus 3x cubed. That is something that's true, right? If you do something minus something and then subtract the other way, everything just changes signs. And then we actually have to do the integral. Yeah, we do have to do the integral. I think they end up being pretty much the same since they have the same kind of limits and the same. But let's check. So here I'm going to get 3x to the 4th over 4 minus 12x squared over 2 is 6x squared. From -2 to 0. That's going to be 0 minus 3 times 16 over 4 minus 6 times 4. Or just plugging in the -2, sorry. And then over here, we'll get 6x squared minus 3x to the 4th over 4 from 0 to 2. If we plug in 2, we're going to get 24 minus 3 times 16 over 4. 16 over 4 is 4, 3 times 4 is 12, 24 minus 12 is 12. This is going to be 0 minus -12, which is also 12. So we end up getting 24. It isn't always true. It isn't usually true that these areas are the same amount, but the way we often come up with these problems, they often end up being the same because of some background symmetry that is not immediately evident. All I'm trying to say is they don't always end up necessarily being the same. So don't think that's going to happen every time. All right. Grab this other example here. Yeah. All right. So I think. Yeah. All right. I'm just going to keep doing examples. You guys stop me if you got questions. I get my volume on, right? Yeah. I do these kind of funny, like in Dr. Burke's class right before this, she'll ask you guys for questions, and she'll really be like, all right, someone has to have a question because I know you guys are asking me all kinds of stuff. So somebody better ask a question. We're not doing anything else until we move on. Like, it feels like she really I appreciate it. I think that's good that she really encourages you guys to ask questions. But sometimes it feels like maybe no one has a question, which is okay. And then the student's like, all right, I guess I'll figure out something to ask so we can move on. But anyway, if you have questions, please do ask them. But I know you guys want to see examples, so I'm just going to keep moving. But really stop me if you have something. So let's find the, we'll set up anyway. Maybe we'll find the integral. Let's set up the integral for the area between, what have I got here? So this is going to be a little bit more complicated. Y equals x squared, y equals 1 over x, and also x equals 9. X equals 9, y equals 9. When you've only got two functions, it's easy to, maybe not easy, you don't have to draw a picture because you can just say, okay, they intersect in these places and that's it, you're done. But when you've got more than two functions, it really does become a having to draw the picture kind of situation. So we really do want to draw the picture here. Fortunately, it's not too hard to draw any of these. Let's see. So, y equals x squared looks like your usual parabola, bounded by, or with 0, 0. 1 over x is a hyperbola. Looks like this. And they intersect somewhere. And then y equals 9 looks like a horizontal line. So that's actually interesting. Interesting. I hadn't thought about that. Yeah, okay. There we go. So without that clarification that it's in the first quadrant, we actually have a problem. The problem being there are two valid areas that have those three functions as bounds. This region here has this bound, and this bound, which would be a valid way of describing this. So does this region here. So, right, if someone says your area is between these three things, it has to have those three things and nothing else. So it could be this one, but then we're saying it also has to be in the first quadrant. So let's erase the other quadrants. I don't want them. Okay. So now it's a little more clear that it has to be this region here. Do be careful though, because I've definitely seen people pick the wrong region. Like I've seen people like, oh, it's this region here. It's not this region here. This region has the line x equals 0 as a boundary. That's not on our list. So just be aware, right? The region that they're describing has to have all of the functions as boundaries and no other functions as boundaries. So you can't say this has to be a boundary if it's not included in your list. Okay. So there's two ways to do this. There's the kind of more normal way, which normal where we're going to use vertical rectangles. The problem with this is that here and here, the heights of the rectangles are different things. Right here, the height of that rectangle is the top function, 9, minus the bottom function, which is x squared. Whereas here, the height of the rectangle is equal to the top function 9 minus the bottom function, which is 1 over x. That means we have to do two integrals. So we need to figure out, well, actually we need to figure out, we probably should have found all the points of intersection. Sorry, due diligence. So finding this point of intersection, we're setting the two functions equal to each other. So this is where y equals 9 and y equals x squared intersect. So x squared equals 9, x is going to equal positive 3. Could also be negative 3, but that's over here. We don't care about that. This point here, where 1 over x equals x squared, you could do the math, but I know you all know what the answer is. What does x have to be for this? can show me on your fingers. You can type it. Just don't give me the middle finger. Anybody? You guys just pretending to be there? Yes, thank you. It is 1. Right, if x is 1, 1 over 1 is 1, 1 squared is 1. You can also multiply both sides by x and say 1 equals x cubed and then get 1. But a lot of the times, these problems are, well, I should say, a lot of these times, these problems that are not on WebWork or WebAssign are designed in such a way that the limits of integration are nice and easy to find. That is not always the case for the computer generated problem. Sometimes limits of integration are kind of terrible. So take it with a grain of salt. If a human has written the question, most of the time they've tried to write it in a way so that the points where the things intersect are fairly nice. This point up here is maybe an exception to that. If we set 9 equal to 1 over x, so 1 over x equal to 9, then x is going to be 1/9. So that point there is 1/9 common 9. All right, so here's what we have to do. We have to break this up in the middle. Well, middle. So from x equals 1/9 to x equals 1, we have to do 9 minus 1 over x. From x equals 1 to x equals 3, so this, this region here, we have to do 9 minus x squared. Which is not terrible, right? Both of these integrals are totally doable. But most of the time, if a math person says, do this the easiest way possible, the implication is they want you to use one integral. Meaning, if you're getting 2 doing it this way, you have to switch your orientation or the way you're thinking of things. We have to use horizontal rectangles instead of vertical rectangles. So let's look at the other orientation of this. I'm not. Go ahead.
How do you know where to draw the rectangles? Like, how do you know? Like, right there. Like, why?
I could have drawn them anywhere.
Oh, okay.
The only thing I knew to do, the only distinction I was making is that I was separating between the right side of this and the left side of this. So that on the right side, the bottom function was x squared. On the left side, the bottom function was 1 over x. But no, I could have drawn. I could have just.
Okay.
I could have drawn this one like right here, and said the height is still 9 minus x squared.
They're just like representing what the.
Because really, so here's the truth. What I'm actually thinking of is I'm drawing all the rectangles. I just don't want to draw them all. So really what I'm doing is I'm saying, okay, this area here is all these tiny little rectangles, right, added up together. Right? And so each of these rectangles, the base is dx. And the height is, well, for these rectangles, the height is 9 minus x squared, where x is anything from 1 to 3. So when x is 1, the height of this rectangle is 9 minus 1, which is 8. When x is 2, the height of this particular rectangle right here is 9 minus 2 squared, which is 5. So this rectangle is height of 5, this rectangle is height of 8. But the way we get them all is by doing the integral. Okay, so let's look at the other way of thinking about this. So we draw the same region. Same point of intersection. But now here's the idea. Instead of using rectangles that are vertically oriented, we're going to use rectangles that are horizontally oriented. The advantage to this is that in this region, all of the rectangles have the same boundaries, right? Here, the height of the rectangle was the top minus the bottom, but in this section, the bottom was 1 over x, and in this section, the bottom was x squared. Here, to find the height of the rectangle, it's going to be this minus this, right? That's your height, which is going to be, so when your rectangles are vertical, like on the other side, you find the height by doing your bigger thing minus your smaller thing, right? Your top minus your bottom. If you do it the other way around, you'll get a negative value, right? You always have to have bigger values minus smaller values. So to find the height here, well, if we have to do bigger values minus smaller values, which is bigger? The thing further to the right or the thing further to the left? Let me ask that differently. What's a bigger x value? The thing further to the right or the thing further to the left? To the right, right? Right. Yeah. So for vertical, it's top minus bottom. For horizontal, it's right minus left. And the base of your rectangle is no longer dx, right? Dx is a small change in x. This is a small change in y. It's dy. This is a clue. This is a clue that tells us, oh, our variables have to be y's, not x's. So when we start integrating this, the area is going to be given by the integral of something dy, if that's your base. The height is right minus left, but we have to change the functions to be in terms of y. And so if y equals 1 over x, I'm going to solve for x. I'm just going to take the reciprocal of both sides. 1 over y equals x, or x equals 1 over y. And then for this function here, I'm going to take y equals x squared and solve for x. Now, when you solve this, you do get x equal to plus or minus the square root of y. This side here is the plus side, because it's where x is positive. This side over here that I erased, that would be x equal to the negative square root of y. But over here, this is x equal to the positive square root of y. So my right-hand function is x equal to the square root of y. My left-hand function is x equal to 1 over y. And my limits of integration have changed as well. Before, the limits of integration were x equals 1/9 to x equals 1, and then x equals 1 to x equals 3. Now my limits of integration are how low we go to how high we go. So basically, on the other side, I'm thinking about how my rectangles can slide. If it's a vertical strip, it can slide left and right. On this side, these horizontal strips, they can slide up and down. How low can they slide? Down to a y value of 1. How high can they slide? Up to a y value of 9. Questions about this? Let's actually do this one since it's not terrible, right? So if we integrate this, that's y to the 1/2. The integral is y to the 3/2 divided by 3/2, which is times 2/3. minus the natural log of the absolute value of y from 1 to 9. And then if we plug this in, we're going to get 2/3 times 9 to the 3 halves minus 2 natural log of 9 minus 2/3 times 1 to the 3 halves minus the natural log of 1. Okay, natural log of 1 is 0. 1 to the 3 halves is 1. So I get 2/3 times 9 to the 3 halves is 27. I've got 2/3 times 27 minus the natural log of 9 minus 2/3. So it's 54 minus 2 is 52/3 minus the natural log of 9. Which might not seem very nice. It's not. But I will say that doing the calculation this way is much less work than doing it this way. This is not, I mean, I might be exaggerating a little bit. It's definitely less work. It might not be much less work, but it is less. So that's kind of the idea with this sort of example is you're going to have, people are going to want you to be able to do this. I feel like I've got another example somewhere here. Yeah, oh yeah, let's look at this one. Sure, let's do one more of these. Let's see, what else did we say today? Oh yeah, okay, cool. I can wrap it back around. I'm smart. Sorry, where'd you go? There we went. Set up an integral for the area bounded by. Yeah, so let's be super extra careful here. So we want the area bounded by. So it's bounded on the right by y equal to x squared. On the left by y equal to 8x. And above by y equal to 16. Let's draw the thing. It's not too terrible to draw. But we do really have to draw it. So here's y equal to x squared. Maybe not my best drawing ever. Here's y equal to 8x. It goes to the origin. And then eventually these are going to cross again. But I'm not going to worry about that too much. And then y equal to 16x. Sorry, y equal to 16. So here's what it said. We want it bounded on the right by y equals x squared. So y equals x squared should be the right-hand boundary. Okay, it's looking good. So this is so our region is somewhere over here. 8x should be the left-hand boundary. Okay, so it's somewhere in between 8x and y equals x squared. And bounded above by y equals 16. So this should be the top boundary. So we want everything below. So that's the region we're looking at. And just like the previous one, oh, sorry. Yeah, sorry, I missed that, Emma. Yes, totally right. Yeah. So for this one, and we're going to see the same thing happening here, actually, that we're going to ignore the negative square root of y. This one, we could do, so words. We could do this as an integral with respect to x, which is where you use vertical rectangles and dx. But if we do that, we're going to have to split it up there. Because in this region here, the tops of our rectangles are 8x and the bottoms are x squared. Over here, the tops of our rectangles are y equal to 16 and the bottoms are y equal to x squared. And while that'll be perfectly fine to do, we can totally set this up as the integral from 0 to, oh, where do these intersect? At x equals 2. I'm just setting 8x equal to 16 and getting x equal to 2. We can totally, this is the integral from 0 to 2 of 8x minus x squared plus the integral from 2 to where do these intersect? X squared equals 16, so x equals 4 of 16 minus x squared. People are going to ask you this, like, so here's what I would say. If you're more comfortable doing it this way, you should do it this way. But what's probably going to happen is someone is going to say, you must change the order of, or you must change it to the other variable. Yeah, sorry, I'm thinking of slightly different wording here. But yeah, you have to integrate with respect to y. Someone will probably ask you to do that. So we have to be able to do it the other way. Let's try again. Here is our stuff again. This point here is 2 comma 16. I know it's x equal to 2 because I set 8x equal to 16. This point is 4 comma 16. So we set x squared equal to 16, we get x equal to 4. Or negative 4, which will be over here, right? Okay, fine. And then finally, this point here is obviously 0, 0. So now we're looking at using horizontal rectangles for this whole entire region. And you can see it doesn't matter where you draw the horizontal rectangle, the right-hand boundary is always y equals x squared. The left-hand boundary is always y equals 8x. There isn't some top being different here than it is here. So the area of a rectangle is, again, base times height. The base is your dy, and just the thickness. Oh, sorry, my ear just started hurting for some reason. That doesn't feel good. Anyway, sorry. The thickness of the rectangle is your dy, and the height of your rectangle is the bigger value minus the smaller value, the right minus the left. But again, we have to change them to functions of y, not functions of x. So this one here, this y equals x squared, becomes x equal to the positive square root of y. This here, yes, would be x equal to the negative square root of y. But we're totally ignoring it because that's not part of the region we're looking at, just like in the last problem. And then this here, y equals 8x, we would solve for x and we would get x equal to 1/8 y. So the area of a rectangle would be right minus left, so root y minus 1/8 y times dy. That's the area of just one rectangle. And then the total area, we add up all the rectangles. So the total area is going to be the integral from, we'll feel that in a second, square root y minus 1/8 y. How low do my rectangles go? How high do my rectangles go?
16.
Thank you. Most of the time, you're going to get different limits of integration. Occasionally, you'll have some funky thing where like they're the same either way because like it's the region from 0, 0 to 1, 1 or something. But 9 times out of 10, they're going to be very different limits of integration. So yeah, that's kind of the gist. Oh, I have 1 minute left. Let me just say, so I was going to do a different example, but let me just Let me try and throw one more. I know we're almost out of time, but I just want to say one more thing. Let's say we wanted to answer this question. What's the average value? I know she talked about this at the end of class. Average value of f of x equal to, sure, let's do, sorry, I had a good example, now it's gone. Let's do x sine of x on the interval from 0 to pi. Average value is super easy if you know how to integrate. The average value is just, it's the integral of the thing, and the only thing that makes it the average value is that you divide by the length of your interval. So if you know how to integrate, you know how to find average value. You just find the integral and then divide by however long your interval is. So in this case, we'd have to do integration by parts. We'd have u equal to x, du equal to dx, dv equal to sine of x, v equal to negative cosine of x. So this would end up being, so usually people, instead of dividing by this, they say multiply by 1 over pi. So we would say this is equal to 1 over pi times u times v, so negative x cosine x, minus the integral of v du. So minus and minus is plus cosine x dx. I guess I really hate writing the limits of integration here and here. I'm just gonna write them at the end. I know it's kind of weird notation, but it's okay. And then we would get 1 over pi negative x cosine x. Integral of cosine is sine from 0 to pi. So then it would be 1 over pi times, let's see, when I plug in pi, I get negative pi times cosine of pi plus sine of pi, which is 0, minus negative 0 times cosine of 0 plus sine of 0. 0 times anything is 0, sine of 0 is 0. So we end up getting 1 over pi times negative pi times negative 1. So here's what I want to say before I write the final answer, which I know is 1. The area under x sine of x from 0 to pi is pi. I don't know exactly what it looks like, but it looks, I don't know. It's like, it's, so here's pi. Maybe it's something weird like that. I don't know. The area under there is pi. The average value is pi divided by the length, which is also pi. A student described it to me this way. Think of it as an ant farm. You guys know what an ant farm is? I had one when I was a kid, like many years ago. And you know, like the ant farm, like, you know, is this rectangle. It's like kind of like, ooh, like that. If you shake it all up, it levels out. And that height, that's the average value of this function. It's how much, it's how high it would need to be to have the same amount area, but all be at the same height. So that's what we've got over here. This region, it has an average value of 1, meaning if you took another region with the same length and have the height be 1, that area and that area would be the same. But long story short, calculating the average value is very easy. If you know how to do a definite integral, all you do is divide that definite integral by the length of the interval from a to b.